Now, having talked about the physics, mechanics of fracture, the next thing to naturally to move towards is fatigue. So we are going to talk about fatigue crack growth. So basically, the idea is that you take a structure with some crack in it and you apply a load that is not so large, so that, in other words, for this given crack size, the moment, let's say, I'm applying by bending this plate, it's less than the critical value of the bending moment. So the crack does not propagate catastrophically. I don't seem to have fracture. But then what I do is, after loading it, I remove the load, and then I load it again. And then I remove the load, and I do it again. I remove load, remove load, remove load. And it turns out that if I do this enough number of times, I don't know how many times I need to do it. It depends on the amount of moment I'm applying, the load that I'm applying. Eventually, this crack, I can observe visually or perhaps under a microscope that it sinisterly and slowly will increase in size. So that's the initial size of the crack. If the size of the crack increases as the crack propagates, if the crack propagates as I do this, then the bending moment that I was applying, which was smaller than the critical value to begin with for that initial crack size, might actually be large enough to cause fracture, because now the crack propagates and then the moment I'm applying for this larger crack size is actually the critical moment, and eventually fracture will occur. So the physical observation that cracks eventually grow under loads that vary with time, so you load and unload, for instance, is eventually an important issue in the mechanics of materials and when we design things. So to summarize, essentially one observes experimentally that suppose you have a constant load, it could be tensile loading as well. Here I'm just writing P, which does indicate tensile loading. It could for sure yield. So far those are the two failure issues that we are concerned with, or it could fracture, and with fracture there is going to be some associated critical crack size. But suppose I design the structure such that I know there is any crack that is present in the structure, possibly present, is less than the critical crack size for that load, and that load does not cause yielding. So I have a safe design for a given load, which is constant in time. Okay, but then we take the safe design, and the only thing I change is I cycle the load that we are applying. So here the keyword is cyclic loading. And eventually, there are many ways to cycle the load. Let me just tell you one. This is called 0 to max loading. Okay, so you increase and then decrease, increase and then decrease. And if you do this enough number of times, then you notice that the structure that you thought was safe actually is not safe. It was safe for static loading, but here we have dynamic loading. Now dynamic loading should be carefully assessed or understood in this context. Dynamic could also mean that I load the structure with impact. Okay, static is slowly loading, impact would be dynamically loading as well. Here what I mean by dynamic or static is static, nothing changes over time. Dynamic, the loads change over time. They don't need to change over time in an impact fashion. They just vary over time. with some, say, frequency. So this issue, the fact that a safe design under static loading fails under dynamic loading, loading that varies cyclically, and 0 to max loading is one example, is called fatigue. And I have already given you a hint as to why fatigue occurs. The reason, it turns out, is crack growth. So cracks, any crack that might be present in the structure will eventually grow, and this is experimentally observed if you cyclically load the structure. Now the question is, which crack, right? Now, if I design something, why would I want there to be a crack? And if there is a crack, is that design, is that structure permissible with respect to service? Now that is a critical question, actually. So first of all, there may be cracks in the structure, already present cracks, that you may or may not be able to detect. So sometimes, so for instance, you are manufacturing the crankshaft of a car, and if you do eventually your summer training, what is done actually regularly is that people check the surface of the critical portions of the crankshaft, where it eventually connects to the pistons, where the surface has to be very smooth, etc. And eventually they do an inspection. There are different ways of inspection. One of them is a manual, a visual inspection. And if they see somehow a crack, and this looks like a non-standard scenario, they immediately discard the piece. So it's not something you want to carry on into the manufacturing line, right? So if you see a crack, perhaps you don't want to use that piece any further. Now, however, what might also happen is the following. Well, how do you detect if there's a crack or not? You need to do some inspection. How do you do the inspection? Well, you do it visually, or you use an instrument. Now, either visually or using an instrument, any type of measurement has a certain resolution. So for instance, suppose I have an instrument, but this instrument cannot measure cracks of size less than 1 micrometer. If it's larger than 1 micrometer, as I scan my structure, it will tell me, oh, here, there's a crack. Or perhaps there's a crack over here, I don't see it with my eye, but the instrument tells me that there is a crack at that point, and it's of size 3 micrometers, whatever, right? But if there is a crack in that structure, and that crack is less than the resolution of the instrument, then in this case less than 1 micrometer, the crack is there and my instrument does not recognize it. It thinks that there is no crack. So there might be always cracks in the structure that we may not be able to detect. So we may detect them or we may not detect them. If we cannot detect them, that has to do with the resolution of our instrument, for instance, and we call such a crack size AD. So this is the minimum detectable crack size. Okay, so, and now there was actually a crack. I thought it wasn't there, but it is there, and sinisterly and slowly it will grow over time, and believe me, for any given load, eventually it will reach a size where it will cause failure. Now, this might be one scenario. Another scenario is there might actually be no crack. Okay, so suppose you do an extremely well regulated manufacturing process and there is no crack, but a crack has a definition. It's like a void with a very a thin geometry, almost like an ellipse that has no thickness. That's the way, in fact, we have derived it when we were talking about fracture mechanics. That's the way we defined a perfect crack, an ideal crack. Now, however, there may not be a crack. There might be a tiny void in the structure. There might be imperfections. A void would be, let's say, like a almost spherical cavity. A spherical cavity is not a crack. The stress concentration is not infinite. So there might be imperfections, and a void is one of them. And such imperfections are always present. Always present in a structure. And these act as stress raisers. So the stress in the vicinity of the void is actually larger than the stresses slightly away from the void, and eventually these stresses could be sufficient to cause local failure of the material, and this local failure could accumulate to an extent that eventually a crack starts to form in the vicinity of the imperfection. So for instance, if this were a brittle material and the stress concentration due to the imperfection, due to the void, exceeds the ultimate strength of the material, locally there could be a crack that forms during loading. And as soon as that crack forms, you're back to the first scenario. You have a crack and it will grow over time. So even though you think you may not have any crack, and in fact there isn't any crack, a crack might nucleate. So one way or the other, you end up with a crack. And that crack will grow due to the cyclic nature of the load, and it will cause failure for a load even that under static conditions would not actually cause cracking. Okay, would not cause fracture. So this is the scenario that we would like to now analyze. This is a very, let me say, still clean scenario. We are going to monitor how a single crack forms. In reality, in a structure, there are many cracks, different shapes, different places, experiencing different loadings. We're going to look at a very ideal scenario, single crack that eventually will grow over time. And as we move into this type of physics where we look at how things vary over time and how the imperfections grow, these the mechanisms that govern the physics of crack growth and eventually fatigue are rather complicated, and to this date nobody can say that they have a absolutely full understanding of what is going on. And for that reason, the topic is heavily guided by experimental input. So remember, even the beginning of fracture was highly mathematical. We were able to write down the stress field in the vicinity of the crack tip, and based on that we actually formulated a failure criterion through the stress intensity factor. As we move more and more into the region of cyclic loading, into fatigue, we're going to start working with more and more empirical relations. In other words, relations that do not necessarily rely on nice theories like elasticity, but rather heavily on experimental data. So just keep that in mind, that fatigue is quite empirical. Right, now let's try to slowly put into equations what it is that we are trying to do. So, and in the meantime, we're going to start introducing some terminology. So the first thing that we are saying is that our load is not a constant. The load actually varies over time. So the way we can quantify time is either time itself, or because we're talking about cyclic loading, we can count the number of cycles. So in other words, I load, that's 1, 0 to p back to 0, that's 2, 0 to p back to 0, that's 3, p to 0, 4, etc. So each one of those is a cycle. So I can count the number of cycles, and that is a typical way with which one quantifies a time in fatigue. So the absolute time, so in other words, whether you go through, say, 10 cycles in 1 hour or let's say 1 day, might actually have an influence to the physics. In some cases it does. We're going to look at scenarios where the absolute time that is associated with the number of cycles is irrelevant. eventually when we talk about viscoelasticity, we will see that absolute time plays a significant role in the physics. But in this case, in this type of fatigue physics, we're not going to look at the influence of absolute time. So we're just quantifying time with the number of cycles. And what we're saying now is that we have a load, and let's write the magnitude of the load here, and that's our stress. And if you like, this is like a gross stress. That's why I have used S here. Gross stress on a fractured specimen. We apply a load that causes this gross stress to vary over time. Now, I'm going to choose again a 0 to max type loading because that's what I have initially started with. The max value of the load is indicated by this blue line, okay, the dashed line, and the load starts from 0, goes up to a certain value. That's one cycle, the second cycle, the third cycle, etc. There will be eventually many cycles, hundreds of cycles, thousands of cycles, perhaps millions of cycles. We don't know yet. So now we have a fracture criterion, first of all, and I'd like to write that over here. We have a fracture criterion that says that, well, if I write the value of K1, which is the form factor times a load, multiplying root pi a, and omitting the safety factor, if this is equal to the fracture toughness, and I'm assuming mode 1, then fracture will occur, right? Now, the first thing I can do is I can look at the most critical fracture scenario that I can possibly have in this, associated with this blue loading. The most critical scenario that I can have at any point in loading is when I reach the maximum value of the load. That's where this becomes a maximum. So when S is a maximum, the corresponding size of the crack to cause fracture is the smallest possible, okay? So, and the smallest crack that causes fracture is, in some sense, the most critical crack. So the critical crack size that we can define for this type of loading is associated with the maximum load, right? Now, on the other hand, at any point in loading, right, let's say at that point, so I load, I go to S max, and if the crack is of size AC, then fracture would have happened, right? But if I am below the maximum load, even if the crack is close to AC, I'm far away from fracture. So these are the critical points, and when S is less than S max, even with AC, I wouldn't get cracking. Now, however, on the other hand, I remember that there is a physics that I'm considering, and that's the physics of crack growth. And so initially, the crack is actually far from being even close to the value of the critical crack size. The critical crack size, let's say, is 1 millimeter. Initially, the crack that I detect or may not be able to detect is, say, 1 micrometer, okay? And so because the crack is much less than the critical value, even when I go to the maximum value of the loading, I will be far away from the value of the fracture toughness, so I will actually be safe. So let us say that this is the initial value of the crack. Now, what is the initial value? Again, let me emphasize, the initial value is either the value that you detect, okay, or the value that you cannot detect. So if there is a crack, you see it, and you want to monitor its growth, you know its size, you take that to be the initial crack size. But you do an examination, you find no crack, okay, or there is a crack and you cannot detect it. In either case, because you're doing an examination, you probably wouldn't be able to detect a crack that is going to nucleate a little bit later in the vicinity of the void. In either case, if you don't see anything, then you have to assume that your instrument is not able to detect this crack size. So you have to assume that there is possibly a crack of size AD in the structure, just to be on the safe side, because if it's there, you wouldn't be able to detect it anyway. So AI is either given, or you have to assume that it is equal to the minimal detectable crack size. And now the physics of crack growth says that over time, and now time is number of cycles again, this crack will grow. So initially it's AI, but over time the size of the crack will grow. So that's A. And at some point it will reach the critical crack size. Now, if it is equal to the critical crack size, then we know that as soon as you reach the value of S max at the, say, 1000th cycle, fracture will occur, right? Now, we are interested in eventually the question of how many cycles will it take to failure. So you may quantify that number of cycles. You may be interested in the number of cycles for the crack to grow from initial size to the failure value, or for that matter, in general, to any other value, from some initial value to some final value. I'm interested in how many cycles it will take, for instance, for the crack to grow from 1 micrometer to 5 micrometers, okay? Or I might be interested in the number of cycles it will take for the crack to grow from the minimum detectable crack size to the value of the critical crack size, AC. So AI, AF are quantities that you eventually pick according to your concerns. All right, now let's have a look at, therefore, a little bit, a number of additional issues. And the first thing we can notice is, well, at the beginning, the crack is much smaller than the final crack size, or in this case, the critical crack size. Okay, so it's much smaller. So because it's much smaller, so A is much, much less than AC. So let's write that over here. For any given crack size that is less than AC, so for instance AI, this could be AI or AD, I can calculate a corresponding value of the critical load. That would cause fracture if I had increased the load for that crack size to that value. So in other words, for instance, initially the crack is of size AI. If at the very first load I had increased the load all the way up to the corresponding SC for that crack size, then I would get a fracture. Okay, the crack would catastrophically propagate. Now, as the number of cycles increase, the value of the size of the crack will increase. As the crack size increases, to maintain the equality, the critical value of the load, the maximum load you could actually apply, which you're not applying, but what you could apply, will keep decreasing. So the critical value of the load that you can apply will continuously decrease. It will decrease until there will come a time when the size of the crack will increase towards AC, and when A is equal to AC, the load that causes failure will be equal to S max. When A is equal to AC, the load that causes failure will be S max. So when the green line hits the value of S max, it continuously decreases. When it hits that value, you get failure. So this is the number of cycles to failure. Number of cycles for the crack to grow from its initial size, Ni, to the final size, NIF. So that's how we are going to denote it. Number of cycles for the crack to grow from the initial size to the final size. The load varies 0 to some S max. At any stage before I reach that, S max is not going to cause fracture because the size of the crack is less than the critical size, but the crack is growing, and there will come a point when the crack is large enough for fracture to occur. At any stage of loading, I can actually increase the load to a value. The maximum value I could apply is SC. For any given crack size, there is a critical load that I can apply, which is always larger than S max. I don't apply this in practice, it's just that I could, and eventually that load will decrease because the crack is growing. When that load is equal to S max, then I get fracture. That's another way to view this issue. Now, based on these concepts, now we can define a number of safety factors. One safety factor you could possibly apply at any stage is to assess the criticality of the situation with respect to loading. So you could define a safety factor that says that my safety factor with respect to loading is SC over S max, which is always greater than 1, right? So in other words, so I have a plane wing, right? And the plane wing actually contains a crack, and you know that it's there, and the plane under flight conditions experiences the maximum load. You expect it to experience a maximum load of S max, but it goes into turbulence, and all of a sudden, although you expect it to experience S max, the load shoots up to a certain value, and you like to assess how much it can shoot up, how safe you are. So the largest it can shoot up to is SC. You expect that to happen. If this accidentally happens, then your safety factor against failure would be XC. So that's the idea of introducing the green line. Another safety factor you could talk about is the safety factor on life. So what I could do is I can at any stage quantify the following. Well, I've just said that the number of cycles to failure is here. This is NIF. Okay. So NIF is the maximum number of cycles I could possibly apply. So in other words, I take my structure into service, I keep cycling it, and suppose I know that the number of cycles to failure is 1,000,000. Now, I don't want to cycle it to 1,000,000. If I try to cycle it to 1,000,000, it means that I am assuming a safety factor of 1, right? Suppose I know it will fail at 1,000,000 cycles, and I do the following. I cycle it to 999,999 cycles, and I stop. I'm one cycle away from failure, and I think that I'm safe, right? But we know it doesn't work that way in real life. There are always a lot of things that we can not account for perfectly. So we want to be on the safe side. So we put a safety factor. And with that safety factor concept comes in a concept of a service life. So in other words, what you're going to say is, okay, I suppose know that I can cycle the structure through 1,000,000 cycles, but I want to do that with a safety factor of 10. So in other words, if I reach 100,000 cycles, I better stop, because with a safety factor of 10, I'm about to fail, right? So when I reach 100,000 cycles, and it would be, let's say, over here, and hats, so this is service. When I reach and hats the service life, then I stop and do something. Well, what can you do? You can either repair or you can replace the part. Okay? That's why you take your car to the service, so that they do something about it. They probably have certain safety factors that are written in their service manuals, and they say that, okay, the so-and-so part, let's say the chain that connects your camshaft to the crankshaft, whatever, needs to change after so many kilometers or years, whatever, right? So that has to do with fatigue. They want to make sure that eventually you're sufficiently far away from failure to within a certain safety factor. Okay, so that is eventually a practical concern that comes out of all of that discussion. Now, let me take this thing into a box, because it's eventually going to be critical. My concern is going to be a very simple question. And my question is the following. I have a structure and it has an initial crack size. And I know the geometry, I know the crack, and I know how I am going to load it. I know the blue line. And I ask myself the following question. I want to cycle this thing. I want to put it into a process, a design in which it will experience cyclic loading. And I want this structure to eventually be safe to within a safety factor of 5, 10, whatever. When should I do the service? Okay, so if I know the safety factor, and if I know the number of cycles it would take to failure, if I can somehow predict it or measure it, then I could calculate n hat. If I know that, right? If I know this, and if I know that, I can calculate this. So then I can tell you, okay, are you going to use this piece in such and such application? Then you better service it with a safety factor of 10 after 100,000 cycles, because I know that experimentally or theoretically that it will actually fail after 1,000,000 cycles, right? So that's the practical outcome of that nice equation. So the central question obviously is, what is NIF? Well, to determine NIF, in other words, the number of cycles it would in reality take for the crack to grow from the initial to the final size to cause failure, or to a value at which you deem that the crack is now too critical to maintain in the structure, I need to somehow determine that NIF, and I can do so experimentally, which, however, would be cumbersome. Certainly, I need experimental input in order to formulate some ideas, but just like we've done before, what we would like to do is we would like to model that process. In other words, based on some experimental input, I would like to be able to estimate the following. You give me the crack geometry, you give me the geometry of the plate, whatever, and you tell me what the loading is, and if I know the material, I will be able to tell you what the number of cycles to failure is. And as soon as you know the number of cycles to failure, if you can predict it, then for a given safety factor, I can tell you when to service it. Okay, so you give me your design, you give me your safety factor, I will tell you the service life, right? So that is a very practical outcome. So our goal is to predict, therefore, the number of cycles to failure. That is going to be the central goal of what we're going to start discussing. And the central observation that's going to help us do that is the simple curve that we see here. This curve has a very nice trend. Initially, the slope is very small, and eventually the slope increases. The slope of a line tells us something about the rate of change of this value with respect to that value. So that is a derivative. At any point, if I take the derivative of that line, so I'm going to take the ratio of dA to dN, the incremental change in the crack size with respect to the number of cycles, that's going to tell me the rate of change of the crack with respect to the number of cycles. And what I see is that that rate is initially small, and then ultimately it becomes quite steep. So the crack grows, and it does so at a ever increasing growth rate. Okay, so we're going to put all of those observations together, and we are going to try and formulate a fracture criterion, fracture crack growth, fatigue crack growth criterion.